Okay, so today we're going to talk about electrolytic cells. Remember at the beginning of this unit, we talked about how there's two different types of electrochemical cells. The first of which being voltaic, and those are spontaneous. Those generate their own electricity. Your lab, in the examples that you saw, all of those were able to produce some kind of voltage on their own without outside help. Today we're going to talk about electrolytic cells, and these are cells that require outside help in order to run. Right, so an electrolytic cell is really any device you have, that you need to run using electricity of some kind, whether it be battery operated, or electric plug-in with a cord or whatever. So, the simplest and one of the earliest electrolytic cells was for what we call electroplating. Okay, and the simple idea behind electroplating is, let's say you had some silverware, and you didn't want like a gold piece of silverware because that would cost way too much, but you could gold plate something, and that means coating some other metal with gold, right? So it still looks like gold, even though it's not gold through and through, even though it's some other metal underneath. Okay, so just imagine, let's say you take a spoon, right? And in order to do this, you will need a cell, a solution, and whatever ion that you want, whatever metal you want to coat in this case, the spoon with, you're going to want a source of that metal. So let's say I put a bar of gold. And gold ions are in solution. Of course, you got some inert anion for electrical balance. Now, notice that this is in one cell. This is not in two half cells. Right? The purpose of a voltaic cell in two half cells is so that you can divert the electrical current. Here, we're not needing to do that. We are providing the current. We just want the reaction to happen somewhere. So, we will connect the spoon to the power source, and the power source is going to push electrons onto the cathode. And because it needs a complete circuit, it's going to pull electrons from the anode. Now again, this is a reaction that would not normally happen. We can't easily oxidize gold. I hope you kind of figured that out. Gold, silver, platinum, they don't oxidize easily. And what are we trying to do in this situation? We're trying to oxidize gold to make more gold ion so that we can reduce the gold ion onto the spoon. This is going to be a difficult task to do, so it needs outside energy to do this, right? So after letting this run for a period of time, we eventually will get some gold plating on the spoon. And there you have upgraded your silverware. Okay. It's a pretty simple setup. It's a lot simpler. There's less going on here than in a voltaic cell. We're not concerned with a salt bridge. We have electrical balance because there is only one solution. Okay. So, the other type of electrolytic cell is for what we call electrolysis. All right, electrolysis. And electrolysis means you're essentially taking two electrodes and you're conducting a solution of water, and the electrons will react with the things in the water. So, let's say that we have a copper chloride solution. Okay, so imagine that we have, didn't leave enough room, I'll draw it above here. Here are two electrodes, power source. All right, so we have a copper chloride solution. We got copper, chloride, and the thing we need to now discuss and understand is that water Water is a viable participant in electrolysis. In voltaic cells, we didn't really discuss water because in voltaic cells, water generally doesn't participate. But when you're forcing electricity through water, water all of a sudden now has the potential to be oxidized or reduced, and we have to take account for it. So, like before, let's talk about the things that can be reduced. So we're making a list of the possible candidates for reduction. So at the cathode, what could happen? Well, the things that can be reduced is you can have the copper ion be reduced. That's one possibility. And water can be reduced. So if you think about water and how it could be reduced, when we say water is being reduced, but specifically it's not the water as a whole, it's the hydrogen in water. Because if we broke water apart, remember how we used to, well, sometimes we wrote water like this in the acids bases unit. And the reason why we're doing that is to signify that in water you have the potential for OH minus and H plus, right? So in water, what is it that can actually be reduced? It's the hydrogen. So the hydrogen can go from H plus to H2, right? It can go from +1 to 0. That's reduction. So when that happens, hydrogen will be reduced to H2, and you also have hydroxide, which is kind of just, it's just hanging out and left over from before. So the reduction potential for water is negative 0.828 volts. Now, everybody take a second and take a look at your reductions chart. So something to point out. Water is on this chart twice. So if we said that the reduction potential for water is negative 0.828, does everybody see where that is? The half reaction for the reduction of water, okay. So water is listed down there. It's below the zinc, above the manganese. Everyone find it? Okay. What I want to point out is scroll up near the top, 5th line down from the top of your chart. You see water again, but the difference is this. On your chart at the top, what you are seeing is the reduction of oxygen to form water. Or in other words, you're seeing, and then back to the notes, you're seeing this reaction in reverse. You see, when we consider what are the possible oxidations, water is always a candidate for oxidation and reduction. So here, when we consider what are the possible things that can be oxidized, well, water can be oxidized, but what in water can be oxidized? Well, we mentioned that we consider water as H plus and OH minus sometimes. Specifically, it's the oxygen that can be oxidized. Bless you. So because your chart is not an oxidations chart, it's a reductions chart, that is why you see the reduction of oxygen to form water up so high. Because the oxidation of water on your chart would have to be that 5th line, but it would have to be reversed. Okay, I'll say that again. To find the oxidation potential for water, you've got to take it off the chart, but you're taking that reaction and you're flipping it. Okay, so what is the oxidation potential for water? It's a number and a sign. Well, what's the number?
0.83 volts.
No. We're taking the higher one. Oxidation. The oxidation of water is the 5th reaction flipped. So the sign listed on your chart is positive 1.23, but that is listed as a reduction. So to get the oxidation of water, we have to put a negative sign in front of that. So it's negative 1.23. Okay, these two are very different. Do not get them confused. You're going to use the top one when you're referring to the oxidation of water. You're going to use the bottom one when you're referring to the reduction of water. Okay? So, when we look at this solution, this copper chloride solution, and we say, what could possibly be oxidized? Well, chloride here could be oxidized. We could take chloride and turn it into chlorine, Cl2, right? And so the oxidation potential of chlorine, again, you go to your chart and you find chlorine's reduction and you flip it, and that's why here it's listed as a negative 1.36. Okay, so those are the only things present in this solution. We've identified what the candidates are for oxidation, what the candidates are for reduction. And to determine what actually happens, you take the higher in each category. Okay, so the highest in each category, well, in the reduction is this one. Okay, so that tells you that the reduction reaction takes place is the reduction of copper. And now for your possible oxidations, you take the highest oxidation potential, which is this one. So your overall reaction then can be determined. Overall, the reaction would be Cu2 plus 2H2O forms copper solid plus, oh, there's a number missing here. There's a 4 there. Plus 4H plus O2. What is E cell? All right, well, E cell is E-ox plus E red. Right, we said that E-ox was negative 1.229 and E red is positive 0.339. So your overall cell potential is going to be a negative 0.89, which is perfectly okay because what type of cell is this? This is electrolytic, and what do you know about electrolytic cells? They are non-spontaneous. They will not happen on their own. For all electrolytic cells, you expect a negative voltage. Okay, so let's take a step back here. An electrolytic cell is very, very similar to a voltaic cell in terms of how you figure out what's happening. It's the same process. You list your possible oxidations, you list your possible reductions, and then you choose the one based on the highest value in each category. Then you add them up. It's just that in an electrolytic cell, the values will be negative, whereas in a voltaic cell, they will be positive. Okay, so this requires electricity to happen. Okay, so let's consider some other examples here. What reactions occur at the cathode and anode when each of the following is electrolyzed? Okay, molten nickel bromide. The word molten means melted. It means we literally took nickel bromide, the solid, and we melted it down. This is not a solution. This is pure nickel bromide, but it's just melted in liquid form. So we have nickel plus 2 bromide ions swimming around. And that's all we have. So if that is all we have, if there is no water here, water is not a candidate to do anything. So what could possibly be oxidized? Which one of these? Bromide could be oxidized. Okay, so E-ox for bromine would be the opposite of what its reduction potential is. So that would be negative 1.07. Nickel, is nickel on here twice? Nickel actually can be plus 3, but I'm guessing on this chart they didn't want you messing with it, so it's probably not listed. Anyone see nickel on your chart? Nickel 3? No, I don't see it. Okay, so they left it off. By the way, I don't know if I mentioned this before, this chart is not exhaustive. This is not like every single reduction that can happen. These are just the most common ones, right? So just because it's not on here doesn't mean it's not possible. It just means they didn't bother to put it on here. All right, so we're not going to consider it because it's not on your chart. It's not reasonable for you to consider anything outside of this chart. All right, so my possible reduction, well, there's really only one thing here that can be reduced. Reduce the nickel. And so your E red is straight off the chart, negative 0.25. So for total cell operation, look at negative 1.32. And of course, you need to identify what's happening at the anode. So in the cathode, the oxidation is the anode. The reduction is at the cathode. So qualitatively, like descriptively, when you run a cell like this, you should pay attention because you need to make observations. Observations are the clue as to if something is happening. If we're going to see bromine being formed, like liquid bromine, you should see an orange color start to form around the anode. All right, so whichever one we decide as the anode, if this is the anode, we would see orange swirls. Oh, that's too big. Oh, that's all right. We would see bromine being formed. At the cathode, because we are reducing nickel, we would expect an increase in mass as nickel becomes plated onto the cathode. So in our lab, you should be looking for things like this. Okay. Let's do one more, or more than one more. Let's do a couple more. So aqueous nickel bromide. So we have beaker, nickel +3, bromide. And this is aqueous, so we have water. Someone tell me what could be oxidized. Anything in there you think can be oxidized? Yeah, bromine. Okay. Anything else? Water. Let's bring back water. In water, which element is being oxidized? Is it the oxygen or is it the hydrogen? It's the oxygen. So oxygen is being oxidized. That means we get O2. Okay, so the oxidation of water is the opposite of the reduction of oxygen, so that's going to be a negative 1.23. Okay. Possible reductions. Olivia, what could be reduced? Nickel. And that value I can take from 4 E red is negative 0.25. Okay. Anything else? Water. And if we oxidized water, what are we reducing? hydrogen. And E red for the reduction of water, negative 0.83. All right, decision time. What's my oxidation reaction?
It'll be
The highest value of the oxidations, yes. What's my reduction reaction? Nickel. Okay. So the overall reaction then will be, the overall reaction is going to be the same as the one above it, because we're still oxidizing bromine, we're still reducing nickel, right? So in this case, I mentioned this before, but it's worth mentioning again. Oh, you know what? I didn't write the electrons in here. Sorry. Here, let's sneak some electrons in here. All right. So the 2 plus 2 electrons here, and this one was plus 4 electrons here. This one was 2 electrons here, and this one was 2 electrons here. Okay. When we write our overall cell reaction, these are redox reactions, right? We have oxidation reduction. So because it's a redox reaction and you balance this in the half reaction method, you know that you need to equalize charge, loss and gain. So you need to multiply them if you need to. In this case, we have a plus 2 and then 2 electrons gained, 2 electrons lost, right? So we don't need to multiply anything. So the overall reaction is just 2 Br minus plus nickel, 2 plus forms nickel solid plus Br2. But where I was going with that is, if you had to multiply a half reaction by some coefficient, do not multiply the potentials. The potential is intrinsic to the value, to the reaction taking place per electron. It's like a value of density, okay? Just because you multiply a half reaction by a coefficient does not mean you multiply the potential, okay? All right, so we just need to add our numbers together. So we have the same as before, negative 1.32. All right, are you guys clear on the steps? Yeah? All right, go ahead and solve for ALF3. Let's see what you come up with. Determine what's oxidized, what's reduced, what's the overall reaction, what's the potential. What did you guys get? Interesting. Let's talk about it. So, what could possibly be oxidized? Fluoride could be oxidized. Right? And if that's going to be oxidized, we need to find its value and flip it. So we're talking about a negative 2.87. And of course, water can be oxidized. So I'm just going to copy this from here. Okay. What could be reduced? Well, we could reduce aluminum. And the reduction of aluminum would be negative 1.66. Also, water could be reduced. Okay, let's decide. The highest oxidation potential is for water. The highest reduction potential is for water. Oh, okay. So that means, yeah, water is both oxidized and reduced. And so if that happens, your electrode is going to look like this. You're going to see bubbles. Why are we going to see bubbles? Look at your half reactions. What's being produced? Hydrogen gas at the cathode. Yeah. Oxygen gas at the anode. Okay. So furthermore, what's interesting is not only are we getting two gases produced, one at each electrode, but this also has acid-base implications, doesn't it? What do I mean by that? Yeah, you got hydrogen, you got hydronium, and you got hydroxide. So that means if I were to use universal indicator, okay, so universal indicator, if you recall, is green and neutral. It's red in acids and it's purple in bases. Which side is going to be red? Which side is going to be purple? You're going to see swirls of color around each electrode if we mix in universal indicator. So which side is red? Which one? The anode or the cathode? So here's the cathode. We said that at the cathode we are reducing water. If we are reducing water, we're producing hydrogen gas and hydroxide. And hydroxide is blue. So the cathode is going to look something like this. The anode, where we are producing oxygen gas and hydrogen ion, the color is going to be red amongst the bubbles. We use universal indicator often to help us determine which electrolysis reaction is taking place. That make sense? It's pretty useful. Okay, and then the rest of the solution, because universal indicator itself is green, so like the rest of the solution is green. Okay. Okay, let's try this one. Manganese iodide. Tell me what you get. All right. Did you guys get that iodine is going to be oxidized? The water is going to be reduced? Okay. So our overall reaction then, 2I minus plus 2 water forms H2 plus 2OH minus. And then our cell potential, negative 1.36. You need to be able to describe what's happening at the anode and the cathode visually. So which one you pick to be the anode or cathode is arbitrary, but let's just call this the anode because it's here. Call this the cathode. Okay. Any visual indications that we would see by the anode? What do you know about I2? Remember the halogens lab back in unit 6?
Very strong oxidizing agents.
Okay. Color-wise, though.
Oh, purple.
Oh, yeah. So iodine was that's in nonpolar environments. We used hexane and we saw the bright magenta, but this is not hexane. This is aqueous. So in aqueous, iodine is just kind of like a pale brown. Whoops. Brown slash yellow slash orange, depending on the lighting, depending on the concentration, depending how long you run for. Okay, so that's I2. And then what should we see at the cathode? Bubbles. Did you know that Michael Jackson had a pet monkey named Bubbles? He was apparently a fan of electrolysis. Okay, and we did not add any universal indicator in here, so if we did not add any UI, then you're not going to see a color. But if we did, what color would it be? Yeah, it'd be blue. Okay, so the trouble with adding universal indicator to everything is that a universal indicator would obscure the iodine color, right? Because universal indicator is green, and so the green here would kind of make it hard to see the brown, but the universal indicator definitely helps with seeing, the acid or base. So with electrolysis, sometimes you want to do it twice. Sometimes you want to do the same reaction with and without universal indicator, right? So that if there are any other colors to be seen, then you can catch them. Okay. All right, so that's electrolysis. That is how we determine what the reaction is using the potentials. That's how we observe and what we notice, what clues that offers us. All right.